to share my screen now. Let's get this working. And now when I do this with this, oh, you have to give me permission to share. Okay, perfect. So when I do this and I share my screen and go into presentation mode, I can't see any of your faces. So if you have a question at any point during this, please just pipe up. I'm happy to stop and clarify something if you have a question. Big ones, we should probably leave till the end. But otherwise, just please ask me. And I won't see things necessarily in the chat while I'm talking. So I'll try and look for that, but just pipe up if I don't respond to that.
Okay, well, I can moderate the chat as well.
Okay, awesome, awesome. So my talk today is going to be called The Evolution of Galaxies Over the Last 10 Billion Years. And this is kind of an overview of galaxies and then going at the end of the talk into some of the current best facilities and then the future new facilities that are coming that will help revolutionize our understanding of galaxies. I start with this picture. I just absolutely love this picture. It has so much in it. It has, first of all, just this beautiful sky, a sky impossibly filled with stars because it was taken with a camera and not what our eye would see, but reflected off of a lake. And you see so many things in this image. And so when I teach, and I teach different levels, I teach graduate classes, advanced classes, introductory classes, which is what I'm teaching right now, I always like to step back and kind of think about these things in terms of the grandeur of what we're able to look at. And so what you see in this is you see the Milky Way galaxy on the right-hand side. And you all can see my mouse on my screen?
Yes.
Yes, okay, good. And so the Milky Way moves up in a band like this. And if you see these dust lanes running down the center, these black regions over here, and this is something that's cool, I can do a zoom that I can't do, I can actually draw my presentation. These things are dust clouds blocking light from the stars behind them. I'll show you a better view of that later. We also have the two different galaxies orbiting our own, the small Magellanic Cloud right there and the large Magellanic Cloud right there, who were obviously not first seen by Magellan, but by indigenous people in the Southern Hemisphere. But these galaxies were given, for Western astronomers, those names. And so we can see these things as well. And we see all the stars in our own galaxy. Now, what is our galaxy? Our galaxy, if you could view it above, looks something like this. This artist's conception is, in fact, informed by data from astronomers. Our sun is about 2/3 of the way out from the center of the Milky Way, and I'll give you a size scale on this later on. You've got a bar that runs down the middle. The stars and the gas actually oscillate up and down this bar. They go on kind of orbits that move like this through that bar. And as I'll show, likewise, the entire disk rotates. I'll show that in a minute. So, and when we're looking at our galaxy, we're looking at an edge-on view of this galaxy. So this big strip you see right here is because we're in the plane of this disk looking towards the center. And so our viewpoint in that direction means that when we look in different directions, we end up seeing a big band of light in the sky. And so this is just a gallery of different kinds of galaxies. These are galaxies taken with telescopes in visible light, taken some with photographs, some with CCD cameras. And there's lots of different shapes and sizes of galaxies. There's big, round, fuzzy ones. There's things that look more like that Milky Way type artist impression I showed you before. Then there are big irregular blobs. This is actually the large Magellanic Cloud and the small Magellanic Cloud right there. And things that look like these big edge-on strips. So these are just like a gallery, a rogues gallery of, if you would, of nearby galaxies. And we're going to try and understand a little bit what galaxies are made of, how they're distributed through space, and how they've evolved over time, and how we use different types of telescopes to learn different types of things about galaxies. So if we zoom in at the center of the galaxy, so going back here, we kind of zoom in right in this central region right there. You see an image like this where it's actually flipped with respect to the other one. So actually this star cluster right down there where my mouse is the same as that star cluster right there. This is an image of the galactic center. And what the Milky Way contains is 100 billion stars, roughly, plus gas, mostly hydrogen, but also helium. And the hydrogen is in atomic form and molecular form, so 2 hydrogen atoms bonded together. And it's made of dust. That dust is not the stuff that you sweep up off of your windowsill. It is roughly micron size grains made of silica, carbonaceous grains, iron. And it's very similar to the soot you get from candles. It's not identical, but the closest analog in everyday life is the soot you get or smoke from candles or a fire. But when you get enough of that, it can block the view. So these dark spots are actually obscuring clouds of these small grains that are blocking the light from objects behind them. So how do galaxies internally move? What are the motions of objects within galaxies? So if I just take a single galaxy like this one, it rotates around that way. Now, we would think naively that indeed that would be the direction of rotation. That is, the spiral arms trail the motion of the galaxy. If the galaxy goes in that direction, that these spiral arms here actually trace that out, like you would think of a whirlpool. But it doesn't have to be that way. It could have been the other way around. It turns out that as you understand how spiral arms form, things actually do work in that way. And if I were to take that galaxy and view it instead of face on, view it edge on, I would see that all those stars line up in a line on the sky. And of course, if you were in that galaxy, in the plane of that galaxy, you would see a band across the sky, which is exactly what we see with the Milky Way. Now, this is really cool because you see on this galaxy here, you see this central dust lane going down the center of the galaxy. You see these faint stars up here poking above that dust lane. You see the bulge of the galaxy right there that also pokes above and below the dust lane. And you actually see warps. This galaxy's disk curves down there and curves up there. So galaxies are complicated. They have lots of different components. And I've actually, and this is a different kind of galaxy. This would be an elliptical galaxy in contrast to a spiral galaxy. And in this kind of galaxy, the stars move like bees in a swarm. In fact, this is an awesome image because you see all these little fuzzy blobs in the background here are all other galaxies that are behind this one. Now, there's this really cool video, and I'm going to put this link in the chat window, but I tried showing it earlier, and without downloading the movie, it's quite large, and playing it, it doesn't really work well. So I'm going to just put this in the Zoom chat. This is an image from this is a video constructed from the Gaia satellite. And maybe later we can try and play it or download it. It's about 100 megs at 4K resolution. So I wanted to just hold off on that for now. But that movie shows the individual motions of 100 million stars in the Milky Way as seen by this satellite called the Gaia satellite. So we can use the motion of these particles, these stars, I should say, around the galaxy as a way of weighing the galaxy, because gravity holds all of these objects together. In this diagram right here, there's not, while there is a big black hole at the center of this galaxy that weighs 100 million times the mass of the sun, that is still a factor of 1,000 less than the mass of the galaxy. And so the stars in the galaxy aren't really going around that central mass. What happens is every single particle in that galaxy, just like every single particle in the universe, is feeling the cumulative gravitational pull of all the other particles in the universe, pulling on each other. So we're all connected by this force, this gravitational force that pulls us together. And if you look at the motions of individual stars and galaxies, or clouds of gas in galaxies, you can use those motions to figure out how much mass there has to be to keep everything from falling apart. The analogy is if I take a string and a rock on the edge of the string and I twirl the string over my head, I can figure out, if I know the mass of that rock and how fast it's going around, how strong the string has to be to keep that rock in place. If the string were too weak, it would snap. right? So you can do that. Now, Vera Rubin is an astronomer who recently passed away. She studied in the 1970s the motions of gas and stars around the Milky Way galaxy. So she actually, not the Milky Way, sorry, other galaxies. And so she would actually measure how fast the gas is moving around. And she measured the rotation speed. So the data, and this is a illustration of the data, not the actual data from her paper. What they showed is that as you go farther and farther out from the center, so this axis here is in kiloparsecs, that's right, every parsec is 3.26 light years. So 10 kiloparsecs is 32,000 light years. As you go far and farther away from the center, you find that the matter rotates at about the same speed, about 220 kilometers a second for a massive spiral galaxy. Now, the problem is that galaxies end when you're about 20 kiloparsecs from the center. The visible light at least goes away. And so you would expect that if all the matter in a galaxy were traced by the visible components, the things you could see, that once you got beyond that, there'd be no new mass. And as you got farther and farther away from the matter inside, you would move slower and slower and slower. But in fact, we don't see that. We see that this is flat. And what the implication of this was that missing mass is required. You need extra mass to hold all of that stuff together. Now, you could ask, well, if there's no stars all the way out here, what are you actually measuring? And what she was measuring was diffuse gas. And in fact, if you now go and measure in the radio with hydrogen gas in the midst of the wavelength of 21 centimeters, it's actually the wavelength of light's about that long, you can measure the velocities of this diffuse gas around the galaxy. It doesn't make up really any mass, but it serves as like kind of tracer particles we can use. That missing mass we now know as dark matter. Now, Vera Rubin was the discoverer of dark matter in galaxies, within galaxies. Geez, if anybody should have gotten a Nobel Prize, she should have, but she didn't. She's now passed away, and they don't give Nobel Prizes posthumously. So while we celebrate the recent awarding of Nobel Prizes to people in astrophysics, especially one of the few women who has ever gotten a Nobel Prize in physics, one of now the 5th woman who's ever gotten a Nobel Prize in physics, we have to remember there are other unsung heroes who never did. And since it can't be awarded posthumously, we've missed that chance. But as I'll show later in the talk, Vera Rubin has now been immortalized in a different way by having a new facility named after her. So we believe now that every galaxy is surrounded by dark matter. Dark matter, we know based on its gravitational pull on objects. We've never actually detected it. We think it's a particle. We think it's a particle with mass, but one that doesn't interact with matter or with light, or even with itself. Now, what's an example of this? A neutrino is an example of this. Neutrino is a subatomic particle. There are about 10 trillion of them going through your body every second. They're made by the sun. Big detectors can detect these, but they're incredibly hard to see. They do have mass, but very little. They're not dark matter because we know how much they weigh. We know how many of them there are, and there simply aren't enough to make up this missing mass. So there's something else, something that has mass. We just don't know what it is. We know it's there, though. And people have tried for years and years to come up with alternate explanations for what dark matter could be. Lots of people have tried figuring out whether or not gravity could work differently in our solar system, or we can measure it really well by actually sending satellites out. Maybe it works differently at large scales. And in the end, there's no model yet that can explain everything we see about gravity that doesn't require an extra component of mass, dark matter. Dark matter is necessary for so many different things. I could give a whole talk just on that. That doesn't mean it's the end all be all. We still haven't detected dark matter. Talk about another Nobel Prize. If that gets detected, that will probably be it. But we know that it's there. And so in the Milky Way, it not only has 100 billion stars, gas and dust, it also has lots of dark matter. And if you were, which we can't see, if you were to then do an accounting of all the stuff in the universe, you make a pie chart, just to kind of give us a little humbling moment here. Roughly 70% of the universe is made up of something called dark energy. I haven't talked about that at all yet, but it is an energy that fills the universe that is actually pushing the universe apart. 23% of all the mass and energy in the universe is dark matter. I say mass and energy, actually the energy, the light makes up a negligible fraction of this, so we don't even count it. Hydrogen and helium floating in between galaxies what we call in the intergalactic medium, makes up 4% of all the mass and energy in the universe. Stars make up 1/5 of that. So 1/5 of all the atoms in the universe are in stars. The rest are all in this gas. These neutrinos make up 0.3%. So now you see why it can't be dark matter. And then the heavy elements, the thing that makes up you and me, that's 0.03%. So our whole drama on Earth, all the suffering and happiness and joy and everything on Earth is on a planet whose materials make up 0.03% of everything there is. Gives a little perspective. I study basically this 4.5% of everything. Now, of course, all the galaxies I study are embedded in these dark matter halos. That's critically important. But what I see is this stuff here. How do I see this? I use telescopes. And I use telescopes on the ground. I use the Jansky Very Large Array in New Mexico. I use these telescopes in Kitt Peak just to give a sense of scale. The 4-meter Mayall telescope, it's a 15-story tall building. This telescope is actually bigger in diameter. It's the MMT. There used to be 6 individual mirrors. They called it the multiple mirror telescope. Then they replaced it with a single 6.5 meter diameter mirror. Now they just call it the MMT with no name for the acronym. Just to give you a sense of scale, that's a 6.5 meter diameter mirror. That telescope, which is 15 stories tall, has a 3.8 meter mirror in it. Yet you can see the size scale. That's a door, normal person-sized door. Technology has allowed telescopes to get much more compact. You've used the Magellan telescope in Chile, in the Atacama Desert, as well as the Very Large telescope in Chile. Each one of these has an 8.4 meter diameter mirror. There's the Large Binocular Telescope on Mount Graham in Arizona. And I've also been to Hawaii multiple times, observing on Mauna Kea at 14,000 feet on the Big Island of Hawaii. I'll actually show later some stuff from that telescope there, which is the Gemini North telescope. I don't observe like this, even though I have actually observed at the VLA. When I observe, it looks like this. This is when I'm actually at Magellan. This is my grad student, Minnie Townsend. She's still a grad student with me. This is a grad student who I used to work with at Arizona. This is the observing station that controls the Magellan 6.5 meter telescope. You've got the telescope operator right here. Everything from my mouse over is the operator's domain. They control everything about the telescope. This is the observer station, which you can see blown up right there. It's got a few screens for you to acquire and analyze data. You get a guide camera view right there, and we have our laptops open. And of course, there's a sound system. This looks like it's daylight. It's because it is. We took this during our afternoon calibrations. I also observe from KU's campus. We have a new observing room on KU's campus that allows us to observe remotely with the Keck telescope, as well with a small telescope in San Diego. I've also observed from my laptop. So the way we observe in person is changing. I also use telescopes in space. I have used all of these telescopes at one time or another, either through my own observations or using observations taken from what's called archival data that somebody else took that then I didn't analyze and I use for myself. So ranging from the X-ray all the way through to the infrared. So these have wavelengths of, 10, 20 angstroms. And this here has wavelengths of, 10 to the 5th angstroms for Herschel, right? So big, huge range in wavelengths. And I'll tell you in a minute why looking with all these different wavelengths is important. With the exception of Hubble, the only reason I used all those telescopes in space, because they're much more expensive, is that the Earth's atmosphere blocks all the light except the light in the visible and a little bit in the IR. If you want to look in the ultraviolet or the infrared or the X-ray, you need to go to space. So with all this stuff, what can we see? This is an image of the Andromeda Galaxy. The Andromeda Galaxy is the most distant object you can see without a telescope. And even though I work in my daily scientific life with galaxies that are 12 billion light years away, and we'll talk about what a light year is in a minute, I can go out in my backyard and look at that galaxy. When you blow up that galaxy, it looks like this. It takes the light from that galaxy 2.5 million years to get to us. And again, in a few slides, I'll be talking about that. But that's what Andromeda Galaxy looks like with a modest size. A small telescope, a few-inch telescope even can take this image if you expose long enough. And it's got its own galaxies around it. It's got clusters of stars in it. But if you look at the Andromeda Galaxy in a different light, it looks different. And this is the Andromeda Galaxy now flipped with relation to the other image, taken in different wavelengths. So this is an image taken in the radio, where we're seeing the emission from gas, where the molecules of gas in this particular image, this is carbon monoxide. This is actually carbon monoxide molecules that are spinning, and when they change the rate at which they spin, they let off a photon with a wavelength of 3 millimeters. And we can see that with our telescopes and map out that. And that gas is the gas that ends up being the fuel for star formation. It's the clouds of gas from which stars form. And I'll show a picture of one of those clouds later on. In this image right here, we have the infrared. The infrared is tracing dust that is heat. Again, this dust that's kind of like candle smoke that is heated by stars. And then when that dust glows again, it emits an infrared wavelengths, and we can see that glowing light, and it's a tracer of where the stars are forming. We have our middle-aged stars are represented by the visible light. These are the stars that are relatively unobscured by dust and tend to be older. Now, the ultraviolet shows us young stars. These are stars that are both very young and not obscured by dust, because dust actually obscures things most effectively in the ultraviolet and the blue. So these are the young, relatively unobscured stuff. And if you see, there's an emergent pattern here, which is that you've got this ring right there where the young stars are forming. That ring is traced by that ring in the infrared right there. And it's traced by where the gas is. So the fuel for star formation, the obscured star formation, and those stars that happen not to be hidden by dust all follow that ring. And then the center of that ring is the bulge, which you see mostly in the optical, where older stars emit most of their light. Here in the X-ray, we're actually seeing dying stars. When stars die and become neutron stars, and gas from companion stars falls onto those neutron stars, it emits X-rays. And so you can see these little points are X-rays. Any questions so far? Anybody confused? Should I just keep going for a little bit? Okay, I'll keep going. So how we can look at nearby galaxies, but how can we look into the past? Well, we can do that using the cosmic speed limit. So light moves at 186,000 miles per second. What that means is it takes light time to get from point A to point B. I hinted at this before in my talk, and now I'm going to revisit it. The sun is far enough away, 93 million miles away, where it takes 8 minutes for light to get from the sun to us. So a spacecraft going around the sun takes light a few minutes to get to us. If the sun were to change, it doesn't. It's actually very constant. But if it were to change, let's imagine a solar flare were to go out from the sun. We wouldn't see that solar flare, so the sun changes a little bit, for 8 minutes. The nearest star to ours, Proxima Centauri, is 4 light years away. You may have heard of its bigger cousin, Alpha Centauri, but Proxima Centauri is actually a little bit closer, I think. I should triple check that. But what that means is when we look at that star, we're seeing it as it looked 4 years ago. That means when you look up in the night sky, the stars you're seeing are all in the past. And you have no way of knowing how they look now. You have to wait to see how they look now. You'll never know how they look at the moment you're observing them. You'll only know how they look in the past. The Milky Way is 100,000 light years across. So in that picture I showed you of the center of the Milky Way, many of those stars were 30,000 light years away. We're seeing them as they looked 30,000 years ago. The nearest galaxy, the Andromeda Galaxy, I should say the nearest big galaxy, is 2.5 million light years away. So this object you can see without a telescope. You're seeing it as it looked 2.5 million years ago, before the first hominids left Africa, when the world was a different place. And so our eyes are time machines in the figurative, but also in the literal sense. And if we can look farther away than that, not just the things that are millions of light years away, but billions of light years away, we can see the universe as it looked at an earlier time. And so what I do is I study the universe as it looked in different times in the past, by looking at galaxies at different distances and reconstructing how they evolved from the distant universe to an intermediate distance to the present day. And I'm going to show you a little bit about how we do that. But first, I want to give you a tour of the nearby universe. So this video is really big. I'm not going to embed it. I'm going to show you a YouTube video of it. And I will also put the link to that video in the chat window. So now, actually, I downloaded this movie. Sorry, it was really big and I didn't want to embed it in the plot. So there's a URL at the end and I can send a link to this later if people want. But let me now change my screen share. And now play this. So this is about 1.5 minutes long. Can everybody see this video fine?
Yeah.
Yes.
Okay, so this video is actually made of real images of galaxies placed where they exist in the universe as determined by the Sloan Digital Sky Survey. So they went out and measured the distances to 100,000 galaxies. And they can place those galaxies in a 3-dimensional map of the universe. And then with the aid of a computer, fly through that map where we put the actual image of the galaxy at each point in this map. I did not make this map, but I love to look at it. So you've got galaxies, and there's voids where there's no galaxy. Oh, it kind of ended there. Let me zoom forward a little bit. There, let me play. You've got voids where there's really no galaxy there at all. You've got filaments, so galaxies on these like little tendrils. I'll show you a better image of that later. You've got big kind of clusters of galaxies, like there's a bunch of galaxies in a big cluster right there. You've got walls of galaxies. Galaxies are distributed not in a uniform way, but in a highly clustered way. The same gravity that holds stars together, holds us to the Earth, also pulls galaxies into tight groupings, groups of galaxies like that one right there. You can see these filaments of galaxies. These groups are like beads on a string. And I'll show you an image of this later on in my talk. Okay, I'm going to change my screen and go back to my presentation. And of course, now that I restarted my presentation, I totally lost track of how much time I was spending. But keep me honest, if I'm going too long, just shout out. I normally look at the clock to see how long I've been going, but resetting my presentation through that strategy for a loop. Okay, so that was a fly through of the nearby universe. But we can also now look at a very small region of the universe. And by looking at this very small region for a very long time, look back in time. So this is the constellation of Orion right up on the left. And we're going to zoom in and zoom in and zoom in. And at the very end, you're going to see a small region of the sky where the Hubble Space Telescope stared for 400 hours at one spot in the sky. And now they have to change the telescope image they're using just because they're going so faint that other image didn't really work. Keep zooming in, keep zooming in. And eventually you get to a region that is about as big as the size of a printed period on a piece of paper held at arm's length. And that is this region right there, the Hubble Ultra Deep Field. And in that region, there are tons of little faint galaxies. And I'm going to show a better image of this in a minute. And you zoom in on these little things, and these faint objects are galaxies, some of them with 100 billion stars that are so far away that it has taken 12 billion years for the light to get to us. A better image of the Hubble Ultra Deep Field is this. In this small area, again, the size of a period held at arm's length, there are something like 5,000 to 10,000 galaxies, tons of little dots. I can zoom in on little parts of this image, and all these little dots for the most part, except ones like this with a cross, which is a diffraction spike from a telescope. Those are stars in our own galaxy. That just is an artifact of the optics. You don't see this much from ground-based telescopes because the atmosphere blurs it out, but from space, you see this very clearly. You can see it from the ground. It just really depends on the telescope and the image quality, but it's very apparent from space. All these little dots in these images, these little specks are all galaxies. Galaxies with billions, hundreds of billions of stars in them. And that's just in this teeny tiny part of the sky. These galaxies are billions of light years away. And by looking at these galaxies, we can understand how the universe looked in a snapshot compared to how it was today. And if we compare the galaxies in these images to the galaxies today, they look different. The galaxies in these distant images look very irregular and messy, whereas the galaxies today look beautiful and orderly for the most part. The few irregular galaxies you have, like these on the left, are small. The Large Magellanic Cloud is 1/10 the mass of the Milky Way, but these galaxies are big galaxies. This is what the Milky Way may have looked like 8 billion years ago. And so galaxies were both more irregular in the past, and they were physically smaller than they were in the past. Galaxies have grown in size by sucking in material from their surroundings, and I'll show an animation of what that looks like later. So can we construct models of how galaxies form and evolve? Beatrice Tinsley, an astronomer at Yale who passed away, she was a giant in her field. She died tragically from cancer at a young age, and she developed models of how the stars and gas and galaxies evolve. She, if you know Barb and Bruce, she was actually their dissertation advisor. So they were kind of part of this original crucible of our understanding of galaxy formation. So how do galaxies form and evolve? Well, we start in this idea of how galaxies form and evolve by looking at the conditions as close as possible to the beginning of the universe that we can see. And what we see, if we look out with certain telescopes, is a glow in the sky. That glow is at microwave wavelengths. We call that glow the cosmic microwave background radiation. And that radiation is incredibly smooth. That is, there are variations. If you could look at that radiation and from its spectrum determine its temperature, there are variations in its spectrum that correspond to 10 to the -5 Kelvin temperature fluctuations. A little bit hotter, a little bit colder, a little bit hotter, but only by 1 part in 10 to the 5. And this color scale shows those temperature fluctuations. Red is hot, blue is cold, which if you've ever studied actual radiation, you know is the opposite. We know that cool things tend to be redder and hot things tend to be bluer, but they went with illustrating this more for the public than for accuracy. And every little one of these hot and dark spots represents a small fluctuation in temperature, which in turn tells us about fluctuations in density in the early universe. And these small 10 to the -5 density fluctuations grew under the force of gravity over time to turn into galaxies today. This is from the Planck satellite, by the way. This is an all sky view. I should have explained this. This would be like taking the entire sky and then unwrapping it and putting it on the screen, just like you can take a globe, and by stretching that globe, if you were to slice the globe open and kind of press it onto a table, you could make the whole globe press flat into a map. This is that same thing. It's a projection of the full sky onto a single plane. So if you ask how galaxies evolved over time, you have this Big Bang at the beginning, followed by a rapid inflationary growth in the size of the universe. You've got about 400,000 years after the Big Bang, you've got this glow, which is the cosmic microwave background. There was a period about 400 million years after the Big Bang where the first stars had not yet formed. Stars started, and we call that the Dark Ages. The universe was just filled with gas, but no stars had turned on yet, as far as we know. Then galaxies formed, and over time, galaxies started growing and growing. The universe slowed its expansion down, so the size of this is kind of representative of the size of some region of the universe. And as time went on, that expansion slowed and then started speeding up again, which is this accelerated expansion from dark energy. And we can look back down this tube and see things as they looked in the past. So we can have a simulation which shows us how this might have happened. So I don't know how this is showing up over Zoom, but on the left-hand panel here, we've got a simulation of what the dark matter in the universe looked like, starting from that very weak perturbations, those weak fluctuations in the early universe, and growing over time. I'm going to pause this for a second and explain some stuff. On the right-hand side, you've got the gas temperature. So red is hotter, blue is cooler. These density enhancements are just most of the matter in the universe. They're relatively easy conceptually to compute because they only are following gravity. On the right-hand side, this gets much more complicated because there's gas, gas has pressure, there's radiation that heats the gas can push on each other. So it's a much more complicated. This box is 32 million light years on a side. And there's this number right here called redshift, which tells us how much smaller the universe was back then compared to today. So this is a redshift of 4.6. That redshift is that number z. What that means is that 1 plus that number tells us how big a representative region of the universe is today compared to back then. So this region of the universe was about 5.5 times smaller than it is today, and was about 1.3 billion years after the Big Bang. And this number tells us how many billions of solar masses in stars were in this cube. Oops, I killed the movie, so I'll play it again. So you can see that this matter is falling under the force of gravity into these filaments that connect these dense regions. And as these filaments of structure form, the gas cools. It gives off energy and cools into these filaments. At the nodes of these filaments, these places where these filaments come together, like right there, you get gas of hotter temperature. And you start seeing, maybe you can see this through zoom, little flickers, little flashes. These are supernovae going off in these simulations that light up these regions of space. The gas is heating up as it goes into these filaments. And at the nodes of these filaments, you get red gas, which is where it's very hot. And these are where galaxies are forming. All these little cool nuggets in here, these little blue dots, are places where galaxies are forming in the simulation. And at these centers where you've got lots and lots of galaxies, like those regions right there, you get these huge clouds of gas being blown out of the galaxy at very high speeds. And these dense regions of the universe can be filled with gas that's 1 million or 10 million degrees Kelvin. So now we see as the universe is about 6 billion years after the Big Bang, roughly halfway through its life, the matter has coalesced into these very dense filaments with these voids in between. And the galaxies are flowing along these filamentary structures into each other. And as they flow along these filamentary structures, they are moving through this bath of hot diffuse gas. So galaxies evolve both by growing in size, but they evolve through an evolving universe. And these little nuggets of cold gas that host galaxies in these simulations are actually moving through this bath of hot material. So I'm just going to go on to the next slide. I can always play this later if you want, or I can just fast forward to the end. The beauty of computers. So when we get really close to today, right there, many parts of the universe have emptied out completely and everything else is in these dense parts. And the universe is now filled with this hot gas. Most of the gas is in this hot diffuse form. And this was done by this team of remarkable theoreticians who put together this movie and these simulations.
Did you mention, Greg, how hot that hot gas is?
Yeah, it can be 10 million degrees.
Okay.
So the gas right around groups of galaxies and clusters of galaxies can be 1 million or 10 million degrees. The gas that fills in the gaps between galaxies on larger scales is more like maybe a few 100,000 degrees. So we can think of, does that answer your question?
Yes, it does.
Awesome. So we can think conceptually about how galaxies grow in this really, really complicated simulation. The first thing is dark matter grows. And the dark matter structures grow by gravity. The hydrogen gas cools by giving off radiation from about 100,000 or 1 million degrees into these dark matter overdensities on the left-hand panel, all those little nubs. So we call those dark matter halos. And then within those halos, it forms gas that's about 10 to 100 degrees Kelvin. And that gas is the fuel for star formation. One of the most iconic views of this is one taken from the old instrument in the Hubble Space Telescope called Wide Field Planetary Camera 2. This is the Eagle Nebula right here. Towers of gas and dust are about 3 light years tall. And to give you a sense of scale, these little nubs, like right where my mouse is, the solar system would fit into that nub. So these things are huge. Gas forms from stars form inside of these towers. Now, if you take a bunch of these towers together, they form a galaxy. And this is a galaxy where all these little red regions in the galaxy are actually regions where stars are forming. That red comes from the hydrogen gas that's being heated up by those most massive stars. And all of these together form factories in which stars are made in a galaxy. Now, galaxies don't just make stars by cooling gas. They also put energy back into the gas. This is an image of the galaxy M82, which is a starburst galaxy in which are something like 100 solar masses a year of stars forming in this galaxy. And it has so much star formation and so many exploding stars, it actually blows gas out of the galaxy in this galactic fountain, these galactic winds, which trace these outflows from the galaxy. So galaxies can blow out the gas and self-regulate their star formation. Waiting for my animation to queue up there. Sorry about that. For some reason, my slide isn't animating. There. I don't know what happened, but so I have to go through this again. There. You can also grow galaxies not just by this cooling of gas and this self-regulation, but also through mergers. Two galaxies collide together, and not only does the final galaxy have the mass of the individual components, but also the gas in those galaxies can be converted into stars pretty quickly. And then you can also have mergers of galaxies, like these mergers of elliptical galaxies, that have no star formation associated with them at all. And that's just a kind of simple way of how you can think about all of these complex processes regulating the growth of galaxies. Now, if we want to understand how galaxies evolve, we don't just have to understand those things we can see, we also have to understand the web of structure beneath. So this is an image of the Earth's, of the United States taken at night. And you can see that these bright dots, which are actually posts of light on the planet Earth, they're not randomly distributed through the US. There are big clusters like my hometown, Chicago. There are voids like the Rockies, which some of us said they would not be able to visit for their winter vacation. And galaxies are distributed on these little filaments, right? Now, we could look at these little signposts, these lights marking this map, and from this, figure out that there's this underlying structure. And we could ask a question that galaxies lying in really dense regions of this structure, are they the same as galaxies who evolve in these very, very rural areas of structure? And so this is what I actually study. I study galaxy environment. I study whether or not galaxies in different places of the universe evolve in the same way. And one way I do this is by studying galaxies in clusters. So clusters of galaxies can contain hundreds to thousands of galaxies in them. They are the most massive object that are, this word virialized is actually a really fancy word for saying they're in equilibrium. They don't change much. The galaxies are flying around a lot, but this cluster of galaxies isn't getting a lot bigger. It isn't getting a lot smaller. It's a relatively stable system. Galaxies going into clusters, they go into clusters passing through a range of different environments, just like somebody driving from the middle of Kansas right there. Like, I think that's Lawrence right there. Somebody driving from Colby to Kansas City passes through a range of environments. They go along I-70, then they go through Topeka. They go through, you can see I-70 traced out right here, right? They go, I think it might be Salina, and then Topeka, and then, oh no, sorry. Anyways, I'm going to spend all my time guessing which cities these are. That's Topeka in any case, that's Lawrence, and that's Kansas City, right? So they're passing through bigger and bigger urban centers as they finally get to the big city. And we can ask what changes happen to galaxies as they pass through that region. So this is a science plot that demonstrates that. So on the y-axis here, forget the label, what that y-axis is telling us is the fraction of galaxies that are forming stars as a function of how far away they are from the center of one of these big clusters. And there are a few different people who've done works like this. This is just taken from this one paper in 2015. The red points are the fraction of galaxies in a bunch of clusters. And this limit here is about the same limit as the Milky Way is forming stars. So this is the fraction of galaxies forming stars at least as much as the Milky Way. And random galaxies distributed throughout the universe are this blue bar. And you can see that even if you're quite a far away from that cluster center, so the canonical edge of clusters is that mark, that 1 right up there. Even if you're outside that canonical edge of the cluster, you are forming stars less than in the field. Something about being out in this region makes galaxies look different than galaxies in this kind of average region of the universe. And we can kind of see this if we look at a nearby cluster, the Virgo cluster, and look at it in extreme detail, which is something I've been working on a lot right now. So this is an image of the sky. It's a huge region of the sky. In declination, it goes from about -10 all the way up to 80. And in right ascension, it goes from 100 degrees of right ascension to 275 degrees of right ascension. Every dot in here is a galaxy. And the color scale here is how fast those galaxies are moving away from us, from the expansion of the universe. And without getting into more detail than that, this color coding is a proxy for their distance. The lighter the color of the points, the farther away they are from us, because galaxies farther away from us move faster away from us. This big clump down here is the Virgo cluster. And you can see that around the Virgo cluster are all these threads of galaxies, these filaments. Hang on, oh wait, never mind. I know why I was doing that. It wouldn't. There, these filaments of galaxies, where the galaxies are all roughly the same color in this plot, which means they have roughly the same distance. And they're distributed in this kind of like linear fashion. So this Virgo cluster, this big clump right here is huge. It's got hundreds of galaxies in it. And it's being fed by these filaments, which are feeding galaxies into it. So even when you're far outside the cluster over here, you are experiencing these filaments. And this is a version of that plot. We've actually identified all these different filaments. This is from a paper that we're actually working on right now with colleagues from Italy and France and the UK, different parts of the US as well. And even Germany and the Netherlands are also involved in this paper. So it's a big collaboration. Switzerland, it's a big international collaboration. We're studying these galaxies in these filaments. And galaxies are moving along these filaments into the Virgo cluster, which is actually, we've left out of this plot just to make it easier to see, which is right down here. And you can see the range here is slightly different. So the other plot cut off right where my mouse is moving at around 0. So we were looking at all these things up here before. And so we can explore how galaxies evolve as they move along these filaments. Now, we don't actually get to see the galaxies move. That takes, hundreds of millions of years or billions of years. But we can check how galaxies in these filaments that feed this central cluster right there are different from galaxies at random spots between them. And I'll give an example of a telescope we're using to study this right now. So what are some of the challenges in galaxy evolution? Well, we want to go deeper and further. We want to go wider, and we want to not just look at the stars. So going deeper and further. So we can use different telescopes to go farther and farther back in time by looking farther and farther away. So in the 90s, with ground-based observatories, we were limited only to about the universe when it was twice as small as it is today, about 6 billion years ago. But using bigger and bigger telescopes and eventually going to space, we can now look back to 10 billion years in the past. The next big revolution is going to be the James Webb Space Telescope, which will take us back to a few hundred millions of years after the Big Bang happened and looking at the very first stars and galaxies. So the Big Bang is going to be launched in late 2021. It keeps getting delayed, first because of problems with the instrument and telescope. Now, actually, the telescope is actually great. It's the spacecraft that holds the telescope that had problems. So the astronomer part did a really good job. It's the aerospace company kind of messed up. But then COVID hit. So this is a 6.5 meter diameter mirror. It's made of beryllium with a gold coating. It will sit on top of a big solar shield made of these thin aluminized mylar sheets that are about the size of a tennis court. This thing's huge. It'll get launched to an orbit beyond the moon. It will not be serviceable. It'll have a 5 to 10 year mission lifetime. The first telescope proposal for open use on this is November 24th. And let me tell you, I am working hard writing proposals for this telescope with many teams. There are some public data from some precursor programs that will get made public immediately. One of our faculty at KU, Dr. Alison Kirkpatrick, is involved in one of those. I am not, but I'm going to be putting in my own proposals to use it. I can't wait. Another way to go deeper and further is by using gargantuan telescopes on Earth. These are the next 3 extremely large telescopes that are being built. These top 2 are US telescopes. The 30-meter telescopes, actually, they're both international, actually, but the major share of these top 2 are American. These are going to be through private-public cooperatives, so US astronomers will be able to apply, hopefully, for time on both of these. This is a 24-meter diameter telescope made of a bunch of big 8-meter mirrors. This is going to be a 30-meter diameter telescope. This one will be potentially on Mauna Kea. This one is being built in Chile. And the European extremely large telescope is 42 meters in diameter. Those are cars next to it, by the way, just to give you some size limits. And this will be in the Atacama Desert in Chile. So I am going to be planning on using these, but these things are not going to be coming online until the kind of late 2020s. In the meantime, though, we can do lots of great stuff with telescopes we have. This is an image of the Gemini North Telescope on Mauna Kea on the island of Hawaii. I have just been part for the past 5 years of a big program called Go Green, Gemini Observations of Galaxies in Rich Early Environments. And we are trying to study the most distant clusters that exist to figure out how galaxies in dense environments, where they're packed closely together, differ from galaxies in the present day. And we took this 8-meter diameter telescope and we stared at individual portions of the sky, a little bit bigger, about twice as big on the side as a Hubble Ultra Deep Field. And we stared for 15 hours with these telescopes. And we did this over and over and over again. And in the end, we spent 530 hours with this telescope and its twin in the southern hemisphere, staring at a bunch of these clusters. And when we do that, we can identify in this sea of galaxies, which galaxies are actually in the cluster and which galaxies are actually in front of the cluster or behind the cluster. And so the green ones are things that we've determined are in the cluster. The things with the red circles around them are things that are actually, we found out, are behind the cluster. And so it's been a huge amount of work on this. I can show you another cool result of this at the end if we have time, but I don't want to fall too much behind, so I'm going to leave this here. But I have a plot that shows every single spectrum we've taken in this beautiful montage. You can throw me a request for that at the end, and I can show it to you if you want to. We can also, so this is like the deepest we can possibly go with ground-based telescopes. You're not going to really get more time than 15 hours to stare at a given spot. We did it with 21 different systems all around the sky, different clusters and groups in the distant universe. And now we're getting tons of science out of this. We will in the future be able to go wide and not just deep. This is with the Vera Rubin Observatory in Chile. It used to be called the Large Synoptic Survey Telescope, and they named it appropriately after Vera Rubin. So it is the VRO now, the Vera Rubin Observatory in Chile. I'll show you a real picture of it in a minute. This telescope will have a camera whose field of view is 3.5 degrees. So that's all the moons stretched across the camera. 8-meter telescopes like the one I just showed you have a field of view at most that big. So this will be a huge change in how we can see the sky. It will get 1.5 terabytes per night of data. And in those 1.5 terabytes, approximately 10 million objects will have varying brightness every night. So it's a massive computational undertaking to try and identify the objects varying in their brightness, identify those that are changing because they're just normal pulsating stars, and those that are really interesting, like exploding stars, new kinds of pulsating stars, near-Earth asteroids, counterparts of gravitational wave events, like a whole plethora of things. And so VRO will be doing the Large Survey of Space and Time, the LSST survey. This is an actual image from earlier in this year of the LSST being built on Cerro Pachon in Chile, where the Gemini South Telescope is located. This whole building is where all the computers will be stored to process in real time a lot of that data, and then the telescope will go in there. This telescope will hit the sky over and over and over and over again. And so you can see here a map of how many times each part of the sky will be covered. Many parts of the sky will be covered hundreds of times over the 10-year lifetime of the survey. And some of these little things we call the deep drilling fields will be covered thousands of times over the course of the survey, going insanely deep. The camera for this survey has now been fully assembled and has taken its first image, and fittingly, the first image they took was an image of Vera Rubin. So this is actually the camera. This camera has, oh geez, I knew this number. I believe it's 320 million pixels. I believe, no, it's more than that, it's gigapixel. I'm sorry, I should know this. I actually had this information and forgot to put it in my talk. And I should know this, but anyways, each one of these CCDs is like a 4K by 4K CCD, each one of these little boxes in here. We cannot just go deeper and wider, but we can go deeper and wider. Now, mind you, if you take an 8-meter telescope and take, you know, thousands of 1-minute exposures on this regions of the sky, you're going to go insanely deep. But you can also do it by not only going very deep and very wide from the ground, but also doing it from space. And the next satellite that's going to do this is called the Nancy Grace Roman Space Telescope. There was actually a defense satellite that the government had extra. They gave it to us as astronomers, and we are now converting this into the next generation wide field optical infrared telescope called the Nancy Grace Roman Telescope, which used to be called WFIRST. So Hubble went from wavelengths of around 0.1 microns in the UV all the way out to about 1.6 microns. James Webb starts at around 0.6 microns and goes all the way out to 28 microns. It will be able to see out as back as a few 100 million years after the Big Bang. And the field of view of these telescopes are right there. The Roman telescope will have 100 times the field of view of Hubble over a similar wavelength range. It doesn't go to the ultraviolet, so it's just the visible and infrared. Same size mirror as Hubble, but we'll have 100 times the field of view, but at Hubble resolution. So it'll do the Hubble ultra deep field with 1 million galaxies instead of just 10,000 galaxies or 1,000 galaxies. And the field of view of this telescope is like this. So one field of view of Hubble is something like one of those things. These are the biggest mosaics of Hubble pointings that exist currently, all these different deep extragalactic fields. That is the size of the Hubble Ultra Deep Field I showed you earlier. And the Roman telescope will be this green footprint right there. It'll be almost as big as the full moon, actually as much area as the full moon, but at Hubble Space Telescope resolution by combining 18 4K by 4K detectors. I just had a couple of weeks ago a full week conference devoted to what we can learn about galaxies with this telescope. And it's amazing. And it's going to go up in 2024, 2025. And we need to start, people have been thinking about science for this for a while, but I need to start getting on that and thinking about what I can do with a telescope of this power. You can also go beyond the stars. So you don't just observe the starlight in the galaxy, you also observe the gas. You can do this with a very large array and also with the Atacama Large Array in Chile, which is at the Chanyantur Plateau at 16,000 feet in Chile. This is one of the many, many telescopes. In fact, almost every ground-based telescope I showed you shut down because of COVID. Some of them are opening up. This is one of them. It just had the first people back at the summit overnighting. COVID has really affected astronomy worldwide. Every single observatory shut down. Hawaii was one of the first ones to open up. The Chilean observatories are just now starting to open up because Chile was really under strict lockdown for a long time. Arizona's telescopes are also now just starting to open up. We may actually be able to observe there in the spring, although we're not quite sure who will go and how we'll go. And we don't want to sit next to each other in a control room. So there's all these things we have to think about and how we can observe. Anyways, that was a side point I hadn't anticipated talking about. If you take these telescopes and you look at the gas, you learn very interesting things. This is an image on the right of the antenna galaxy, the center of the antenna galaxy, where you see two galaxies merging, and you've got these bright stuff from the stars right here, and this dark stuff in between. And if you actually were to look at this, and you would think, oh, most of the stars forming in this galaxy merger are these bright regions right here and right here. That's where it's brightest. That's where most stars are forming in this collision of galaxies. Turns out if you actually look in the dust and the gas, what you find is that there's a bunch of stars forming right there. This is the dust and gas where stars are forming, and the dust that's glowing from the re-emission of stars. And you find that actually the most luminous part of this galaxy is that right there. And if you overlay these, you find that the most luminous part of this galaxy, where most of the stars are forming, is this area between those two bright nuclei of the spiral galaxy that are merging to form this one. So unless you look in the gas, looking at the emission of molecules, you actually don't even get to see where most of the stars are forming. So I'm working also with data from the VLA and also from the ALMA telescope, the Atacama Large Millimeter Array as well. So if we have all that together, we can have a movie now, just to end the talk, with a movie of how an individual galaxy would form if you could actually combine all the stuff we've been learning about galaxies and put it into one of these complicated simulations. So on the upper left-hand corner, you have that number Z. So if Z is 4, that means the universe is 5 times smaller in this simulation than it is today. The rate at which stars are forming in solar masses per year is in that box right there, in this big box. And this is the formation of a big giant galaxy today. And it's what we would see if we could see this with a telescope. So the red is from red stars, and the blue are forming stars. The galaxies form by these lots and lots of little tiny pieces coming together. And as these galaxies build up their stars, they get redder and redder as the stars within them age. You can see this galaxy is a beautiful spiral galaxy within it. So as this galaxy is forming, it's having a spiral inside of this swarm of red stars. And these things are pulling together over time, over the force of their own gravity. New galaxies are actually forming. Gas is collapsing and forming new galaxies in the outskirts of these big ones. That galaxy didn't just form, it just popped into the little slice that was this simulation. And now all of these galaxies are merging together in one giant, huge, chaotic free-for-all merger, where the stars are getting disrupted, the gas is getting converted into stars, and all the gas in this system is now being used up in these rapid bursts of star formation. And what you are left with is an elliptical galaxy. This big spheroidal distribution of stars that accretes new galaxies over time. So this is a galaxy with lots of blue young stars. And over time, this thing just grows to be this pretty somewhat boring blob, but that formed from this remarkable history of galaxies living, dying, getting shredded apart, and merging together. And so I try and study all of these different processes by looking back in time. Just let this run to its end. And the simulation, again, is done by this group called the Illustrious TNG team, another group of really good theoreticians. So that was the last slide of my talk, or this is the last slide of my talk. So what's the summary? Well, galaxies evolve. They look different in the past than they do today. We can observe this evolution using big telescopes. We've seen that galaxies are different in different parts of the universe. Galaxies in the outskirts of clusters look different from galaxies in the insides of clusters. We can simulate how galaxies grow using the knowledge we've gained from our observations, and new telescopes will revolutionize our understanding of all these things. So with that, I am going to stop and stop sharing so I can